Oh. Well,
Oh no.
Let's hear
We
more
said
about that.
life-changing events, so
Tell us more.
it's a snake plant. I got it for $10 from Walmart.
What's its name?
Bob.
That's cute.
Yep. Came with it.
It came with the name. The name came with the plant.
Yep.
Unfortunately, you don't get to rename it.
Yeah, I couldn't do that to the plant.
Cool.
I got the thermistor board to work. Yay. That's life-changing.
That's awesome, dude. We've been
Yeah.
working on that for like a year.
Yeah. Honestly, though, like most of the work, like most of the credit goes to Jazz and Yash. Like I just had to plug some things in, and then it worked immediately. Like I didn't need to do that much. So
That's perfect.
I really don't know why it was taking that long.
It's cool that like so many different people contributed to it.
Yeah, like 5 at least.
Yeah.
And
yeah.
Is that actually like you ran through like all 3 boards, all channels? They seem to be functioning.
No, so far I only have the bottom board and the middle board is what I'm using, and I've only tested like 2 channels, and they both worked. So I'm gonna probably continue testing like every channel and make sure that everything is working as it should. But we can talk about that in the embedded meeting.
Cool. Anybody have any questions from last week or the week before? So we went over, what did we go over? Data inputs, right? Also, this is a point where most people would apologize for bad handwriting. I'm not going to, because I'm proud of it. So you're welcome.
Never
we had
apologize.
pull-ups. And yeah, Jared's writing is so nice and beautiful in his lessons, and then I come here and scrawl little scribbles. Oops, and pull downs. Outputs we had. Anyone want to remind me, what did we have here?
Gabe, I can't see your screen.
Oh no. Thanks. So on inputs, we have pull-ups and pull-downs. Outputs, yeah, a little reminder, please. There's two types.
Push, pull, and open drain.
Thank you. So push-pull, you said you can push your output up to 1 or pull it down to 0. Open drain, usually just pull down to 0 and then let it float. So you often need to use an open drain in conjunction with the pull-up resistor so that your states are defined properly. And there are a lot of great applications for this, some of which we mentioned before, but the common is sharing the same line and making sure that each player that wants to interact with that line doesn't accidentally cause a short. We also played with the idea of an active low signal. This is very common. You'll see in embedded and in the electrical realm, especially if you're working with microcontrollers. So as the name implies, It's a signal that is active when it is low or grounded or sending 0 volts. All of those things mean the same. And common ways to see this written. In your schematic, usually you'd see an N here, or you'd see a hash symbol, or you see a bar on top. And then some people also put a little mini N in front. These all mean the same thing. It means that when that pin and that signal is sending a 0, which is equivalent to a 0 volts, then the line is active. It's doing what it says it's going to do. So in this case, reset whatever it's connected to, maybe a microcontroller. And we're sending a 1. Depending on the logic high of that microcontroller, of course, could be 3.3 volts or 5 volts. It is inactive, so it's not doing what its purpose is. So it's not going to reset the microcontroller. Great. So let's move on to topic of today's lesson, and that's analog. This is a pretty different sort of application. And it's interesting because from what we know of these little mini computers, they like to speak in zeros and ones and in the digital world, right? But the world manifests itself, at least electrically, as analog. And we mentioned that analog is almost like an infinite set of values, right? So if we kind of split this in half, woo, it's fat. Let's split this in half. So this would be our analog side. This is digital. And analog, you can almost see, you can take on an infinite set of values within the signal range, and digital, a finite set of values, right? You can't exactly match all those infinite little divisions, but it can kind of get close, breaking it up discretely. So the way this works is usually we use what is known as an ADC, right? So ADC stands for analog to digital converter. Extremely clever and innovative name. It's named after Mr. Analog to Digital Converter, so that guy's famous now. But the way it works is essentially doing this, right? Converting our infinite sets of values into a finite set. And that sounds easy enough, right? It's hard to go from a finite set of apples, for example, to an infinite, but it's probably easier to go the other way. I think there are some questions here. Wow, Mahmoud. Spent 25 seconds looking for questions, and it was this. So, like we said, we're going from almost like this infinite to finite, which is kind of a weird concept, but essentially all that's happening is, let's say I have a signal, right? And it can go from anywhere from 0 volts to 5 volts. Let's say it kind of looks like this, right? So maybe this is a microphone, right? The way a microphone works is it uses a pressure sensor to sense changes in pressure around it. And as you're speaking or singing into it, that pressure fluctuates, and that manifests itself in different voltages that the microphone is reading. So in your microcontroller, you want to read the microphone and understand exactly what the person's saying into it, and digitize it, right? You want to maybe record what someone is saying, or you want to distort it or modify it or play it back at a higher volume, for example, on a speaker. So what your microcontroller needs to do is sample this signal, right? And essentially what we do is we say, okay, I may not be able to exactly cover every single little bit of voltage here, but I can try, right? I can do a fixed amount. So this is an extreme example, but let's say the microcontroller can break it up into different sections. So let's say I can read something that's 2.5 volts, 5 volts, 0 volts, 1.25, and then 3.75. So I have 4 different steps, right? And this is a digital signal. Remember that digital just means we have a finite set of possible values, right? So what this would look like is probably some really poor approximation, right? So I'd have maybe something like this signal will look something like this. This guy, 175, into 1.25, back up, move to 5, down to 0, 2.5, 1.25. So before, where my signal was like, I kind of like overlay them. Super nice and continuous. I actually miss a lot of information that's happening here, right? Because I've digitized it into certain fixed values, right? So you can imagine, what if I had more values to play with, right? What if instead of just having these 4 sort of levels, or I guess 5 levels, 0, 1, 2, 3, 4, 5, what if I had 10, 11, 12? Well, you just get even better, right? So if I have suddenly a bunch more values, I can then, this is going to be hard to draw, apologize in advance, but I can then step a lot more smoothly, right? And I can get a lot of these more subtle transitions in voltage. And I don't have every single value in between. Again, I have like a little step, right? So it's not going to be perfect, but it's going to be a lot closer than what my original guide looked with only 4 steps, right? And this is what they call analog to digital conversion. And so this idea of having a certain number of steps and increasing that number of steps basically comes with how sophisticated your analog to digital converter is. So it's a little box, ADC. And usually it's a little piece of silicon inside your microcontroller, right? So you're going to have a chip, like let's say this is our TMS570. There's pins around it, right? That's how we interface with the world. Within the TMS570 chip, there's going to be a little piece of silicon inside called an ADC. And that's going to do this conversion for us. Now, this notion of splitting it up into different little chunks, that's what's known as the resolution of your ADC, right? So resolution is a term commonly used in sampling and digital signal processing, usually where we're trying to get a really good measurement of the world around us. And if you have a higher resolution, that means you have a more precise measurement. You're able to get more information from your measurement and break up your analog signal into smaller and smaller chunks. If you have a very low resolution, then you don't have as much granularity in how you can measure a signal, right? So we talked about up here, we only had 1, 2, 3, 4 different levels plus 0 volts. Over here we had a billion, right? Obviously I'm exaggerating, but the more resolution you have, usually the more expensive, right? So higher resolution usually comes with higher cost. But again, better measurement. So it's a trade-off, of course, as most things are. The more resolution you have, the better you can approximate what the world around you is doing. So usually the way people like to specify this is in bits. So a common thing you're going to see is I have an 8-bit resolution for my ADC. And what this means is that, so first let's look at what an 8-bit number looks like. So 1 bit is essentially a 0 or a 1. If I have an 8-bit number, I have 8 of these bits. And remember, we're working in binary, right? So each of these bits can be 0 or 1, right? So I have 2 options for each of them. If I had something like 0, 1, 0, 0, 1, 1, 1, 1, that's an 8-bit binary number. And each place, like we said the other day, is a placeholder for a different category, right? The same way in decimal, each spot is like the tens, the hundreds, the thousands. It's a similar concept with binary, but the base is base 2, right? So the number of possible combinations we could have is related to the number of bits we have possible, right? So 1, 2, 3, 2 to the 4, 2 to the 5, 2 to the 6, 2 to the 7. So I could have a number that is 0, 0, 0, 0, 0, 0, 0, 0, right? And then I could have all zeros and then a 1, all zeros and then a 1 in a different spot, all zeros and then 2 ones. I could have all of the different combinations all the way up to 1, 1, 1, 1, 1, 1, 1, 1, right? It turns out that the number of total combinations I could have is actually equal to 2 to the number of positions I had. 8 in this case. So 2 to the 8 are the total number of possible combinations I could have in an 8-bit binary number, right? So 2 to the 8, what would that be in decimal? Well, right, 2 times 2 times 2, right, 8 times, just 256. If I do math wrong, please yell at me. Very bad at arithmetic. But this means that we have 256 possible different values you could have for an 8-bit number. So if our ADC is 8-bit resolution, you can imagine that what they're trying to tell us is that we actually have 256 steps, which is actually really good. Right, 256 different little steps that we can use to digitize our signal. And so while we don't get the infinite set of possible voltage values that exist in analog, in digital we're getting pretty close, right? Whereas if you kind of squint and look at it from far, you're going to be really close at approximating your signal, right? And to tell you the truth, I forgot what our other signal looked like, so I'm sure this looks different. But until you kind of zoom in, if we were to zoom in this little chunk, right, it would kind of be looking like this. But if you kind of look at it from far and squint, it's pretty close. And so this is an 8-bit resolution, right? So how many steps would we have for 10-bit resolution? Someone yell at me, please. Give me the answer. Yeah, I think I saw a couple in there, right? So 2 to the 10-bit resolution is 2 to the 8 times 2 times 2. So 256 times 4. 4 times as many steps, right? So the higher you go in resolution, the better you're going to be able to divide your signal into discrete little chunks. And this is a super useful concept, and it's something that we use everywhere in the car, right? The way we understand what's happening in the vehicle is by measuring things, right? So we want to sample things like our current, right? We want to measure voltages, like battery voltages, for example. I swear this isn't R. Ugh, battery voltages. We want to measure temperatures, right? And these all manifest themselves as analog voltages. So to be able to act on any of these, we need to sample them with our microcontroller and split them up digitally. And correct me if I'm wrong, Mahmoud, our TMS-70 ADC is 12 bits, is that right?
Yep.
Yeah, so we're lucky. Yeah? This is a pretty nice resolution. So we have 4,096 different little levels that we get to play with. And it's interesting because depending on the voltage range of your signal, your 4,096 little steps are gonna split differently, right? So there's a concept called the analog voltage reference. So an ADC will have, usually it'll have a power supply. So this actually provides power to the silicon to turn it on and to perform its operations. But it also has an analog voltage reference. And similar to how we had this logic level idea for GPIOs, right? We said that, as an aside here, for a GPIO and for a microcontroller in general, but your 1 could be interpreted as a 3v3 or a 5 volt. And with some advanced processors that are trying to consume less power, they're even going down to things like 1.8 volts, right? And even lower sometimes. For analog, we have this same sort of concept where it's not a 0 or 1 anymore, but it's this analog spectrum. And so what the analog voltage reference tells you is basically what range of voltages am I expecting or a signal to be? What am I allowing as an acceptable range, right? So your analog voltage reference will define your range from 0 volts up to that voltage. So we'll call it V analog D. Okay, I'm not making up letters. We'll just call it VREF for now. And so VREF is almost anything you want, right? Let's say I only want to accept signals from 0 to 3.7. Right? I only want to look at signals in this range. Then that's fine. What you'll do is you're going to have your microcontroller, right? And remember that the ADC is inside as a little block of silicon inside here. Your microcontroller is going to have a couple pins dedicated to this. So internally, it's going to be connected to some pins, right? One of these pins will be the power supply to actually provide power to the analog to digital converter. And when you start doing layouts for microcontrollers, you're going to realize there are a lot of little pins that supply different modules and building blocks within the microcontroller. We're also going to have a pin for your voltage reference, right? So in green, right? So this, we'll just draw it over here. It's going to be your voltage reference. And what that allows you to do is, with whatever voltage you generate, you can set your max reference for your sampling. And often this is just the exact same value as your power supply voltage, right? Like if I have my 3.3 volts as my power supply, I might just say, hey, I like that voltage. I want to sample things from 0 to 3V3. That's great. You can just connect these pins together and use your power supply as your voltage reference. And that's very commonly done. Usually you're going to have a maximum value, right? You can't put 100 volts on this pin. Your microcontroller is going to get angry if you say, hey, you said it can do anything. I'm going to put 100 volts on the voltage reference, and you better let me sample all of that. It doesn't work that way, unfortunately. Again, the data sheet is where all the answers are held, right? So it'll tell you a maximum voltage you can use as your voltage reference that you can sample up to. And if I remember right, in the TMS 570, it's about 6 volts. Something like that. And so what we do in our car, even though our GPIO logic level is 3v3, on the VCU, the voltage reference is 5 volts. So we are able to measure signals from 0 to 5 on the VCU. Right. And that's just a design choice. It allows us to accept a wider range of signal voltages. A lot of common sensors in these vehicles go from 0 to 5 volts. And so we just have more compatibility that way. Of course, this still means we can read signals that only go to 3.3, right? We can definitely still read these. The only problem is that we're wasting some resolution space, right? If you kind of draw it out. If I can measure from 5 volts to 0 volts, my 4,096 different steps are split between 5 and 3.3, right? Sorry, 5 and 0. If my signal is only going to 3v3, it's only going this way, right? We're kind of wasting this whole region above, where these bits are not going to use. So let's say there's 1,000 bits, maybe 1,000 steps here, in this little top chunk that we're not even using. So our effective resolution, because our signal is only going from 0 to 3.3, the effective resolution that we have is actually only this usable region, right? which may only be 3,000-ish bits. And so it's really important to, if you have the opportunity to customize your ADC for a particular application, to try and match that voltage reference to exactly what you expect your signal to be, right? If I expect my signal to only be from 0 to 1 volts, it's going to be a huge waste to have my reference 0 to 5, right? Because I'm going to be missing about 80% of the total bits I could use, right? Exact same idea as what we just wrote, right? If I'm only going, that signal's only in here, but I've defined my voltage reference to be up here, 4,096 bits that I have to play with. The top 3,000 are not used, right? I'm only using the little chunk here. So you want to be careful. If you expect most of your signals to be within a certain range, then try and maximize for that range. But also keep in mind that sometimes it's a lot more effort to customize your voltage range, right? Usually on a board, for example, on the VCU, let's say I only had to measure signals that were 1 volt, right? Well, to set your voltage range as 1 volt, you have to create that voltage somehow, right? And usually the way you do that is through a voltage regulator. So this is something that Raphael has been looking into and that Jared is going to talk about in a couple lessons, but usually you have a little chip that can create a certain voltage, and usually that's stepping down from a bigger voltage. So on the VCU, we have 12 volts coming in as input to the board, and we use a little integrated circuit external from the microcontroller chip, right? This is on the circuit board of the VCU. So let's say the VCU is this thing. This is a circuit board, right? Printed circuit board, PCB. There's little mounting holes in the corner. You have a little chip. This is the microcontroller part. Remember that the whole board is not a microcontroller. The whole board is just a circuit board around a microcontroller. This is a TMS 570. And so what we have here is that 12 volts is coming in. So this is from the low voltage battery, coupled with the DC-DC from the high voltage battery in the car. And we have little chips on the board, little integrated circuits that generate new voltage rails for us. Remember, we can't just put 12 volts to our microcontroller because that's going to blow it up, right? We can't do that. So what we do is we go through other little chips first. And what these chips do is they step down the voltage for us. So they give us a 5 volts, a 3.3 volts, and actually a 1.2 volt as well. And so this microcontroller in particular is very picky. It needs 2 different voltage supplies. So one, 3v3, that's for all of the internal logic, all of the analog to digital converter modules, for those power supplies that we mentioned to actually turn them on, for the GPIO modules, for timers, for different communication protocols. So it's known as what's called usually the I/O, input-output power. And 1.2 volts is what actually powers the processor. So this is what's powering the actual little computer running inside, the brain that runs the code and that's holding all of the variables and things that you're trying to run. The processor takes this 1.2 volt rail that you have to supply externally, and this is usually called VCC. So if you look in the datasheet of the TMS 570, you're going to see these rails. And because the TMS 570 allows us to go up to 6 volts for the analog voltage reference, we use this for our reference. we use a 5 volt. Right. Mostly because some signals in the car do go that high, and we're not particularly picky about optimizing exactly the voltage range with the range we expect from the signals. And that's largely because we don't know all of them yet. There are still some signals that have yet to be defined in the car, some that we get to choose ourselves. And there's a lot of work that still needs to be done to make sure we have all of the sensing capable. So for example, we don't have a speed sensor yet, which is something we need to look for. Okay, so how did I get started on this rant, right, about voltages? Well, I was talking about the analog voltage range, right? And so, like I said, what if we wanted to be really specific? We were only measuring signals up to 1 volt, right? We said, hey, I have 4,096 bits to play with. The microcontroller gods gave me this. This is a gift that I should use to the maximum of our ability, right? I don't want to waste all of my bits doing nothing, right up here, measuring nothing that's ever going to happen. I'm only ever going to need this little range. And if I set my analog voltage range up to 5 volts, then those 4,096 bits are going to be divided equally from 0 to 5. And then my 0 to 1 volt signal is only going to see a quarter or a fifth of that, right? So I'm sure my math is terrible here, so please don't be angry. Yeah, so a common technique to achieve this, right? So like I said, we don't have a 1 volt rail available, right? We have 12, we have 5, 3.3, 1v2 that we generated, mostly for power to the processor, power for the I/O. 5 volts is actually used as power for a lot of other chips on the board as well. Things like CAN transceivers and other chips that measure current and voltage, digital to analog converters. So we don't have a 1 volt rail. So a common practice is put a chip that gives you that 1 volt rail, right? And usually it looks different. It's not the same as these kind of power supplies that are giving you these voltage rails for power. Usually because these are meant for higher current, right? These are meant to actually consume power to allow things to turn on and run, right? So there's sort of a difference here. So you have those, let's say, voltage regulators. Right, and as Jared is going to mention later, these come in different forms. Raphael knows now things like buck converters and linear regulators, but they're meant for powering things, right, to turn things on. So let's keep it simple, right, to turn things on. Turn things on and supply current, right? So usually they're more expensive and meant for different purposes. And often the voltage precision is not amazing. So they're meant to give you enough current, but the actual voltage you may get out, so let's say I'm getting at 3.3 volts, may not be perfect. You may get a little bit of noise and a little bit of ripple, right? It may go to 3.32, right, 3.28. But usually that's kind of close enough for powering something. For example, the microcontroller is going to have a range of input power, and all it wants is just enough to turn itself on and operate with the current it needs, right? Now think of this for a sensing application where you're trying to be very precise about your measurements. If my voltage range is constantly changing like this, then that means that's constantly affecting the split I have from 0 to my voltage reference, right? So if I put this kind of noisy voltage supply on my reference, I'm going to have a hard time having a consistent measurement. Yeah, I just saw a question here in the chat. If you measure a value greater than your analog voltage range, do you get clipping or overflow? Usually it'll clip, so it'll just max out at whatever your voltage analog reference max is. That's a great question. So let's say, yeah, my reference is 3.3, right? So this is the max I can measure. So it's supposed to be relatively constant. And my signal is chilling and then it goes up. You're not going to measure this, right? You have a maximum that you set your range to be. So what you would see is something like this flat here, and you wouldn't see it that. But like we said, back to this, if my analog voltage supply reference is noisy, this barrier may be changing, right? And so it's not going to be a super clean reference. I'm not going to have a very consistent measurement because that's always changing. And so we usually don't want to use a regulator like this that gives you power for your microcontroller modules and everything that needs power as your analog supply. Usually what people do is use a voltage reference IC. So a separate chip that provides just the voltage reference. Right. So there are different ways to do this. Obviously it adds cost. And in our particular application, for example, we are not measuring so precisely on the VCU anyway that we care about the millivolt difference in voltage reference, but there are a lot of applications where you really do, and you want the most precise measurement you can get. Especially if you want to have a reference that is not one of your power supply voltages, right? If I want my 1 volt reference, I can't use my existing power supply rails that were generated for me, right? None of these are equal to 1 volt. So you just use a voltage reference chip, which does exactly that for you, right? So I have a chip. I give it some input voltage. It gives me what I want out, right? Nothing to it. So this is very commonly used with ADCs, especially in precise sensing applications. And what's interesting is that it can provide almost no current. So before, when we were using these voltage regulators, were sort of meant to handle and supply, current, right? So for our 5 volt and 3V3 regulators, each of these on the VCU can do 5 amps, right? The 1V2 one we have right now, which we're changing, can only do 300 milliamps. So these are meant to provide power to things that want to consume current and turn on, right, and operate. The voltage reference IC is almost like a little flag. It's not trying to provide power or current or anything. All it wants to do is give you that little voltage that tells you, hey, here's the 1 volt reference. Right. This 1 volt reference will allow you to set your analog voltage reference maximum value and make use of all your ADC bits. So, all right. Can someone contact OneNote, please, and tell them to fix this? Because I don't know how. Oh, wow. This is fun. Okay, how do I do this? I hope this is clear. Oh, yes. Right. So we have the 1 volt reference, because this is not helping at all. If we have the 1 volt reference, then usually the current that it can provide is something really small. I'm not sure the exact value, but it's like 5 milliamps. It's not meant to supply current. But on the interesting point is that while it has no current, it has really, really, really precise voltage, right? So it's going to guarantee you a supply that's super tight. You're going to have, you remember that ripple that we had? Okay, I need to get rid of this. Remember that ripple that we had here? So you see this at kind of 3.32, 3.28. It's not going to give you that at all. It's going to be completely solid at 1.000 volts. And depending, again, on how much you're willing to pay for it, you're going to get better precision or worse precision. Right. So it's often that you get to pick exactly what voltage you want. So a lot of the times you get one that looks something like 4.096 volts, right? And if you think that looks familiar, it is, because with a 12-bit ADC you had 4,096 steps, right? 4,096 steps for a 4.096 volt analog reference makes a lot of sense because it divides really cleanly into each other, right? You're not going to have weird little steps of random voltages. It's going to be very clean and obvious exactly what you need. So that's the general idea. That ADC that we've talked about, that's always inside the microcontroller, right? When you start getting more pro, you say, hey, the ADC inside the microcontroller is not good enough for me anymore. I don't like its resolution. I don't like how much power it consumes. I want something super precise. I want something with the resolution that I need. So you move to an external one. So same way that you can buy a chip that has a voltage reference, that generates that voltage reference for you, you can buy an external ADC as well. Right? And there are other reasons why you'd want an external one, which I'll go over a little later. But you can buy an external one and just chat with it, right? And talk to it, and it will do all of the analog measurements for you, right? And maybe it has exactly the characteristics you want that you didn't get to choose with the ADC built into your micro. We'll talk digital, right? And so you have different options. Usually most ADCs internal to the chip are good enough. 12 bits is really useful for us. But there are situations where, let's say, your ADC, you need to sample something far away from your microcontroller, and having the ADC as close to the analog measurement as possible is a lot better. Any questions so far? We've covered a few sort of different things that have gone on here. So we've talked a lot about like the resolution of an analog to digital converter, right? You can have really high resolution, really low resolution. Usually depends on how much you pay for it. Another important characteristic to look at is the sampling rate. So the sampling rate usually is a measurement of speed. It tells you how quickly your ADC can sample the world around it, right? And this is usually specified in something like a number like 10 ms per s. So this would be 10. So this is a particularly fast ADC, 10 mega samples per second. Mega is 10 to the 6, right? This big S is samples. What that's telling you is that it's operating so quickly that it can capture 10 million different changes in voltage every second, right? And so that's important when your signal is changing really quickly. Usually in a high frequency signal, in something analog that is moving really quickly. So let's say I had, some signal that is oscillating at a really high frequency. Right, so let's say it's at, let's make it easy. Or let's say it's at 20 megahertz. That means my signal is sampling 20 million times every second, right? Hertz is just a unit of cycles, so 1 over a second, right? So 20 million cycles per second. Something's going that quickly, and I'm only sampling at 10 million samples a second. I'm only going to catch half of the signal, right? I'm only going to catch once every second period. So I'd measure here, for example. Then I'd miss the next rise and I'd catch somewhere here. Then I'd miss this next cycle I wouldn't get. I have to wait a second cycle and get something here. Right, and I'd only get a certain amount measured. And obviously, if my microcontroller sees this, it's not going to be a great approximation. Even though I have the resolution, I'm sampling so slowly that really all I'm seeing is signal here, right? Signal here, and it stays there, and it stays there, right? It just keeps measuring the same voltage, and then it stays there. My microcontroller wouldn't even see any of these changes or falls or rises because I'm getting a very poor sampling rate. And so it's tricked essentially into just thinking this is a single static voltage that hasn't changed at all. Even though we know we can measure with our oscilloscope physically that that signal is actually changing really quickly. It's just that we only were able to measure certain chunks of it at a time. We only sampled very poorly, right? So an important concept to make sure you take care of when you're working with an analog to digital converter is to make sure your sampling rate is faster than your signal, right? And there are a lot of different formulas for calculating this. Usually it's not a problem if you're working with sort of sensors in our car. Usually our ADC sampling rate is a lot faster than how the signal is changing. But one of the most common sort of rules of thumb is the Nyquist-Shannon theorem. I write theorem like this: TH with a M is an exponent theorem. So basically what this says is that if you have a signal running at some frequency, let's say 100 kilohertz. So if my signal is running at 100 kilohertz, so 100,000 cycles per second. Right, so frequency. Then my ADC should sample at least twice as fast. At least twice. To even have a hope of capturing the signal. Greater than or equal to 2 times 100 kilohertz, right? And often that's still not even close to good enough. But you can imagine. So let's say the ADC operates at exactly the minimum amount. So 200 kilohertz, right? What that means is that for every cycle of my sine wave, for example, for every cycle of it, I get 2 measurements, right? So let's say I get 1 measurement up here, and then 1 measurement down here. And then the next cycle begins. Next cycle starts, right? I'm going to get 2 measurements again, 1 up here and 1 down here, right? I'm measuring at double the frequency of my sine wave, so I get 2 samples every cycle. Now, is this a good indication of the signal? My microcontroller is only going to see these red dots, right? It doesn't know what the analog voltage is. It only knows what the ADC measured and is telling it that these red dots are the only voltage I can measure, right? So what I'm seeing is something like this, right? See the red dot up here, and it goes down to the red dot down here, then up to the red dot up here, down to the red dot down here, right? Looks like a pretty lame sine wave to me, right? So people say 2 times as fast is good, but that's really only to get some indication of the waveform, right? This looks nothing like a sine wave. As far as our microcontroller knows, it's measuring a square wave, right? So a common rule in industry is to be at least 8 to 10 times faster. And more if you can help it, right? The faster you can sample, the better an indication you are going to get of your signal, regardless of how much resolution you have, right? If the signal's changing too quickly, you're not able to keep up with what the actual waveform looks like, right? So if I have a really high sampling rate, so let's say I can do, let's say my ADC is doing 10 times, right? Let's say it's 10 times 100 kilohertz. So it's 1 megahertz or 1 mega sample per second, right? What that means is my sine wave looks like this. Let's say, so this would be 1 cycle, right? From here to here, so 1 cycle. So I'm measuring 10 times as fast, which means I get 10 samples in every cycle, right? So I'd get maybe a measurement here, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And what that would look like on my microcontroller is, okay, I'm reading a voltage kind of here, and step on up here. Right. Now this looks a lot closer to a sine wave, you know? This is still not perfect, obviously, but this is a much better indication of what our signal actually looks like. And that would go on forever, right? You'd get a little kind of digitized version of it. And what's interesting is that our resolution may be allowing us a lot more than just these steps that we're getting, right? We may actually have enough capacity to have measured all the little voltages in between, right? But the signal is too fast for us to have enough time to sample those voltages. The signal has changed quicker than what we can accurately capture. And so you want to be as fast as possible. 8 to 10 times is usually a good approximation, but again, if I can go even faster, that's just better, right? So if I went to like 100 megasamples per second, so I'm 100 times faster. Maybe now my, please, yes. Maybe now I'm sampling so fast that I can really closely approximate the signal, even though it's a little digitized still, right? We have only discrete finite steps that we can measure in. Maybe now I can approximate it a lot closer and actually use the bits that I have and the resolution that I have, right, at its full capacity. And so with what we've been talking about today, we talked about sort of two main concepts, the resolution which is related to how granular, how fine of a division are we able to get of our analog measurement that we're able to digitize into finite values. So on the TMS 570, that's 2 to the 12, so 4,096 different steps. We talked about how this relates very closely to the analog voltage reference, right? This is completely up to you. Even if your ADC is internal to your microcontroller, there will be pins on your microcontroller for you to decide what you want your voltage reference to be. And often a very easy way to go is just use the same voltage as your power supply and expect that it's not going to be absolutely perfect. Or you can go with an external voltage reference IC, right? And that's going to really give you the precision that may be required for your application. Especially if you want your reference to be something that's not one of your power supply voltages, right? Then you're going to need to have one of these because you're going to have to generate that signal somehow. I see, sorry. And they'll usually give you very high precision, for example. Or 4.096, right? And the last thing we mentioned was sampling rate. So this is the speed at which your ADC is sampling. And usually if your signal is not changing very quickly, then it's not a big deal. You check out your sampling rate. Is it above the frequency of your signal? Then perfect. Don't worry too much about it. But if you start measuring signals that may have some high frequency component or that are just changing really quickly, you want to make sure your sampling rate is high enough. And 8 to 10 times is a good rule of thumb, but even that is not going to give you the most perfect measurement. What's important to note is that it's also not just for sinusoidal signals or signals that have some frequency components, right? The edge rate of a signal could also be lost if your sampling rate is too slow. So have a signal so kind of chilling, and then it changes really quickly to go up high here. This transition in edge could happen very fast. So like the time from bottom to top could occur in nanoseconds, right? Nanoseconds. And not every ADC is that fast, right? Let's say we're measuring one here, one here, one here. And then if this voltage range is really important to us, it may happen too fast that we all of a sudden just measure up here, right? And maybe that's fine for you. Maybe you just care about being high or low. But if you really want to have had that information where you're steadily increasing and then up, then you want your signal rate to be very fast to be able to capture all of this edge rate as it goes up. So edge rates are very commonly used in industry as sort of the benchmark for how fast a signal is. And there's some math you can do, but usually it's much faster than the frequency of the signal. And it makes sense, right? If my signal is oscillating, right, let's say it's a square wave at some period, right? This little transition of edge is going to happen in such a short time compared to the whole period that it's going to be so fast. So that often dominates speed calculations if that's something you care about. And if your ADC needs to catch that, then it's got to be usually really fast. But if you just care in this application about highs and the lows, right, then you just need to worry about the frequency of the whole signal itself and how fast that's changing. So you can at least get a couple samples in here, right? At least get a few here, and then a couple down here, and some here, right? Usually that would be fine if you only care about the signal itself. Next week, what we're going to cover is how you do that conversion from analog to digital, very sort of theoretically in code, and then also a couple reasons why we use an external ADC, like the way we're doing it in the car. And then we're also going to touch on the opposite way. So going from digital to analog and how we can sort of achieve that. And that's it for today. Any questions? I need 3 before we can leave, as usual.
What is the upper limit of resolution that's typically found in microcontrollers?
That's a good question. I don't know, to tell you the truth. It definitely comes with cost. So an Arduino Uno, I think, has an 8-bit. It might be a 10-bit. I don't remember. Something like a 570 or a STM32, 12 bits. I think that our BMS analog front end chip, the PL455A, is 16 bits. Is that right, Mahmoud?
$16 bits.
Yeah.
I'm not sure. It's
'Cause it goes
pretty
to,
high
like-
up there though, because it needs very fine. Yeah, I think.
Something like this, right? This number, whatever this number was. Is that the max?
Maybe.
Yeah, I remember seeing
Perhaps.
something like that. Yeah, I could be wrong. I think that's 16 bits. But that's a pretty good ADC inside the chip we're using to measure voltages in the batteries, right? So
Yeah, it is 16 bits.
yeah, cool. Thank you. So depending on the application, and that chip is like $40, right? So you would expect a good ADC for how much you're paying. So you really fine measurements. Now, if you start to go towards chips that are meant for digital signal processing, so there's a whole field of chips called a DSP, right? I'm sure you guys have heard of this before. This is a digital signal processing. Then these are optimized for really fast ADC sampling rates, really good resolutions, and I'm sure they go higher than this, 16 bits. But then again, you pay for it, right? So the highest I've seen usually 16, but I'm sure in high performance industry applications with DSPs, they go up to, I don't even want to know. I think I've seen a 24-bit one on DigiKey once, and I got scared and ran away. But yeah.
It's actually 14-bit.
The
BQ.
EMS?
Yeah.
Okay.
Is it? Are you sure?
I just ripped up the data sheet.
But we're getting definitely the conversion we're doing with 16 bits. And like each cell is like 2 bytes, each cell voltage. So I think it's 16 bits.
Oh, 14 bits plus 2 additional bits created by the averaging.
Okay.
Yeah, so cool. Thanks for the question. 2 more.
There's one in chat.
Oh, thank you. There's such a thing as too much resolution or frequency? I don't know. That's a good question. Probably for cost-wise, you may be paying a lot more than you need to for that sampling rate or that resolution. I don't see how it could hurt you to have too much. Maybe it just makes your processing slower because you have to deal with bigger variables. And your ADC may have a lot more overhead in its like internal processing because it's so optimized for high performance and like a very fine measurement. But I think mostly just the cost. It may also be physically bigger on your circuit board to handle for external circuitry and analog components internally that want that do that super fine measurement. But I think it's just mostly cost.
Yeah, the higher resolution it is, the higher the sampling rate needs to be as well. And it just kind of balloons the cost and the power consumption and all that stuff.
Yeah. Yeah, power consumption is a great point too. Okay, one more question.
What happens if you have too little resolution? Is it just that some signals are missed, like the high level signals?
Yeah, exactly. So if I'm trying to capture a sine wave, it may only look like a square wave, for example.
Right. Oh, okay.
Or I think I have a better. This was for frequency, right? I have a better drawing. Right at the start. Wow, that was big. Yeah, so kind of like this one, right? So up top here we had our analog signal, and we only had 4 bits of resolution here, right?
Right.
You could only get this like very coarse square kind of approximation, but then with higher resolution, get really fine in there. So you're just missing stuff, right? You may miss regions that are important to you.
Thanks.
You're welcome. Okay, thanks guys. We'll see you next week and chat a little bit more about analog then.